Well, good afternoon. My name is Reed Millard. I'm also with the MIT Concrete Sustainability Hub. So we work on a variety of things from buildings to pavements to concrete science, and we're looking at it from a few perspectives. So I'm going to focus on the cost side of things. I'm going to look today specifically at how to incorporate hazard resistance into a life cycle cost assessment. At this point, the life cycle cost analysis that we're doing is more deterministic and for this first phase, and then the next phase we're going to be linking it together with what Josh is talking about so that we can actually underspecify cost as well to influence the early design stage that much better.
Yeah.
Sorry, folks. So while we're at it, just wanted to step back and talk a little bit about the mission of the Concrete Sustainability Hub. We're really working to develop breakthroughs that will lead to more sustainable and durable infrastructure related to, again, pavements and buildings. So we've got a design team that includes civil engineers working at the nanoscale, and then we're working also at the high level, looking at systems level applications. And our strategy to do so is we're really interested in providing a scientific basis for informed decisions related to engineering projects, and we want to demonstrate the benefits of a life cycle view in terms of incorporating all phases, because we know that policymakers and folks within firms are sometimes pressured to look just at that first cost, and we know that that's not always the best case for them. Of course, we want to make use of this research and transfer it into practice, so that's why we're partnering with government agencies and different private groups to implement case studies to see how our tools can be beneficial in practice. And so this is sort of the link between Josh's work and my own, where we're interested in, of course, increasing performance in terms of thermal properties, durability of different infrastructure, but also recognizing that we need to analyze and balance the trade-offs between this performance and the cost and the environmental impact. And we need to have that information up front for decision makers, because although here we really value the importance of environmental impact, oftentimes cost is a determining factor. So we need to have all of that information up front so people can really assess those trade-offs while they're making a decision. Unfortunately, on the building life cycle cost analysis, we don't have to start from scratch. There's an ASTM standard that helps walk you through it and make sure that you're incorporating all of those initial and future costs. It's really rather thorough. It's a pretty accessible document. It's starting all the way from design right through the disposal of the building, so I recommend getting familiar with that guide. And I'm going to show sort of an abbreviated approach here. We're going to be comparing two different buildings in an apples-to-apples way, so I haven't included the design phase, assuming that'll be pretty similar here. And then the scope of our study isn't going to extend all the way to the end of life, so we're going to focus on these first four. So you can imagine, in terms of the cost of a building over its life cycle, really we think about the cost for initial construction, but you've also got energy use. And then what about that wear and tear piece in terms of the maintenance as well as home improvement? And then the hazard repair is going to be the focus today, as we're thinking more about how resilience is a big factor in creating sustainable communities. So let's say you're a designer faced with a choice and you have a client that's wondering, well, I've got the same house, it's in the same place, it looks the same, but what if I go with the lower initial cost and maybe my design will have a worse energy performance, but also maybe it's worse in terms of hazard resistance. The difficulty in comparing those two options is that there's not a lot of quantitative information to help inform that decision, and that's the gap we're trying to fill. So you might be faced with a situation where this R1 lower resistance design standard has a lower initial construction cost, but then over the lifetime we see that it has a higher cost. And of course, we're also interested in comparing those environmental impacts. Today I'm going to focus just on the cost, since Josh has done a great job talking through how we look at the environmental impact. And we found through surveys of architecture firms over a couple of years that the payback period is a metric that really resonates as people are making decisions in terms of designing their homes. Often you'll hear about, should I put a solar panel on my roof or not? Well, what's the payback period, right? So the same sort of terminology is what we're going to use here to think about what's the payback period for designing my home to be more resistant to a variety of natural hazards. And so we're seeing that as the time when the lower standard, the cumulative costs over that life cycle overtake that of the higher standard. And a challenge in this particular space is a little bit around the data characterizing how a particular building is going to respond, how's it going to perform during a disaster. In order to look at a very specific design and compare a lower to higher one, you need to do a complex analysis. And so for this purpose, we've taken advantage of data put forth by Lee and Van de Linde in a study of comparable wood frame homes. And so they chose a 50-year lifespan for their study, and they compared it across 3 cities, 2 which experienced earthquakes, San Francisco and Charleston, South Carolina, and then 2 which experienced hurricanes, again, Charleston and New Orleans. And so they've compared it at 2 different standards here, just like we're interested in looking at. So for the seismic earthquake resistance, they've added more nails in the shear walls, and they've taken a variety of steps in the hurricane case. One thing I've seen throughout several presentations at different conferences looking at resilience is that these hurricane clips are really important. It seems like it's a pretty cost-effective thing. You just need to have a clip to tie your wall to your roof to prevent it flying off in high winds. So that's an example of a little upfront cost that will reduce your life cycle cost. I'm going to walk through somewhat briefly the approach we've taken for these first 3 steps and then focus in on the hazard repair. So to get a sense of how much your building is going to cost to construct, there's several industry used and validated tools such as the RS means, which was used here. We're also using the Craftsman set, and Marshall and Swift is another one that's available. And you can use these a variety of ways. Either if you just have an approximate building design, you can say, I have a somewhat luxury home and it's about this many square feet and it's in this location, and that pops out about the cost of your home. Or if you know very specifically, then you can build it up from the bottom up and say, I have this much wood and this much concrete, and then you can estimate the cost in that way. Again, Josh talked a bunch about the BOPS tool. So if you want to use it just on a one-off basis, you can design a house very simply, and then using your local weather data and utility bills, it'll pop out for you what it expects your utility bills to cost on an annual basis. And I'm very excited about analyzing data in more depth. We've done a simpler analysis here of the Census American Housing Survey. So what that is a survey that the census started back in '73, and they kicked it off again in '85. And they've done surveys of households every 2 years since 2013. And in '85, they started with 47,000 households across the country, and then asked them several hundred questions. And by 2013, 70% of those households were still in the survey, and they added more to represent the new housing stock as the years went on. And amongst those questions were, how much do you spend every year to maintain your house? And also, did you remodel your kitchen this year? Did you remodel your bath this year? Was it a big repair or a minor repair? And with that information, we actually can have a sense of overall in the US how much people are spending each year on their house. We're also going to take that information and convert it into estimates of the embodied impact for those changes to incorporate into the next phase of the LCA tool. So it's pretty remarkable. If we look at the annual spending in 2013 dollars for maintenance and repair, it's been pretty stable over time across all of those households on average. And then from the home improvement, there's a little bit more movement, which you can see on the secondary y-axis over here. That's the housing price index. It's someone just trending with the housing market. As you can imagine, maybe you're not going to put, granite countertops in your kitchen if you think the housing market's going to tank. So, all right, what you've all been waiting for, the hazard repair portion. Here's a little chart from South Carolina where they've shown since 1960 the damages that have been accumulating from a variety of disasters. And though in engineering spaces, earthquakes get a lot of attention towards building resilient structures, we can actually see that a lot of damage is occurring because of hurricanes and tropical storms. So we probably should be putting more attention towards those as well.
That was created in South Carolina, but that's for the whole country.
Indeed, yep. And so I wanted to make you folks aware of two tools that might be useful to you. They're both from FEMA. And on the left, we've got ISSST, and that's a more complex tool. If you watch the news someday and they say, oh, tornadoes came ripping through this area, and then they quote so many billions of dollars, somebody probably ran an analysis of ISSST to get you that estimate. So it's nice because it has analysis for a class of buildings, but if you're trying to do the sort of analysis we're looking at for specific buildings, it's not as helpful. What could be a bit more helpful for that case is the FEMA benefit cost analysis tool, which is actually designed for folks who are applying for grant funding, and FEMA wants to know, okay, you want $100,000 to improve the structural resistance of your building. Well, what's the likelihood that I'm going to get $100,000 of savings in terms of hazard resistance over a time period? So that tool, you can use it for your own purposes to get an assessment for life cycle cost analysis. But again, it's for a class of buildings, so you could say a steel building that's 5 stories, but not my steel building that's 5 stories in this particular location. And so because of that, there's a lot of uncertainty related to decision making in the hazard space because there's specificity in terms of, in this particular location, what are the forces of the hurricane that's going to come pummeling through? How well will my building perform? And if it does get hurt, what's it going to cost? So that's why we're employing probabilistic analysis in that case. So I'm just going to step you through the different components of the model in order to estimate the cost for hazard resistance. So the first thing you need to know is, on an annual basis, what's the likelihood that I'm going to experience a hazard of a given intensity? And so here we are in Dearborn. Here's the likelihood that in 50 years, I'm going to have a 10% probability of exceeding 1.6 to the -2 ground motion in terms of earthquake hazard. Compare that to San Francisco, a couple order of magnitude greater. So we can get that information pretty easily from USGS. On the hurricane side, it's a little bit more difficult because hurricanes just aren't quite as frequent. It's a different way of characterizing it. So in a situation like New Orleans, where you've had a lot of landfalls, they look at several centuries of historical data to build up the likelihood of a new hurricane. In other places where there haven't been as many landfalls, they're going to use numerical simulations. So then we can similarly look, say in Boston, compared to Charleston, South Carolina, compared to New Orleans. You might be surprised that Boston has some high wind potential, but I can attest that during Sandy, my roof budged a little bit on my house, and we had a resident raccoon sneak in. So there definitely are potential in a variety of locations. So once we've got that information, we need to combine that with understanding for different wind speeds, for different spectral accelerations due to earthquakes, how's my building going to fare? What's it going to take to incur minor to severe damage? So based on that study, again, we can look at the lower resistant building and see on the bottom here, we've got minor to more severe damage for earthquakes and hurricanes. And then as we add hazard resistance technologies, we shift so that you only experience this minor damage at a higher wind speed. And a similar story is true for the earthquakes. So now that we know how often a hurricane or earthquake is going to happen and what's going to happen for that specific intensity, we can combine that together and say, for my study period, how much damage am I expected to have? So on the left, for earthquakes, we can see San Francisco with a higher likelihood of earthquakes is going to have more impact than Charleston. And then important thing to note is the difference in the y-axis here, 0.4% versus 30%. The impact and the likelihood of hurricanes is so much greater that we're just more likely to see a higher damage level. And then if you look across that entire 50-year study period, you're almost certainly going to have some minor to moderate damage from hurricanes, but it's less likely in terms of earthquakes. So that's going to influence the importance of this within our life cycle cost analysis. So our next step then is to make those payback period estimations. So the way we do that is we look at it from a cash flow basis. First, you know your initial cost, we've estimated that. Then we've estimated our energy, and we've got some maintenance and home improvement. So I'm just going to zip along here, and hazard damage, we don't know exactly when that's going to happen because it's a random process. So we can discount it to present value and spread it across equally also. So we can see here, if we choose a 3% discount rate versus an 8% discount rate, the importance of these different factors is going to change, and we can see that the hazard impact of hurricanes is much greater than it is versus the earthquakes, and that in the future it matters much less. And then for the higher resistance, your initial cost is higher, but then you've reduced your hazard as you'd expect. But this is a way so you can quantify it and make those decisions. Here we are, percentage-wise, you can see the hurricanes are roundabouts 40 to 60% in the lower resistance and around a quarter for the higher resistance. So now looking at the payback period, this is the metric that we really think is going to influence decision makers. Since they're so unlikely that you're going to have earthquake damage in San Francisco, we're not actually seeing a payback period in that study period. So now in Charleston, we're looking at 16 and 12 years, and in New Orleans, 8 and 6 years. So in conclusion, we want to improve the characterization of those fragility curves so that we can look at a much broader set of cases. We want to improve the characterization of that cost to really capture uncertainty better within there, and I think that that will help improve these analyses as well. Extend the case studies for more locations and designs. And with that, I'll take questions. Thanks so much.
All right. I have a question for you. So it's related to your last statement about expanding the fragility curves. Does that mean you're going to look at building types other than that wood frame structure that you got the data from? So, I mean, how specific do you think the results are now to that building type? Do you expect it to shift around a lot, or is it going to make a big difference?
Let me see if I have. So there is work that's been done, for example, by Florida Public Hurricane Loss Model, where they've compared different building types. I think it will change pretty considerably based on the materials in your system and the location. So yeah, we're interested in looking at it a couple ways, gathering more data from existing studies, but then also potentially building a custom model based on something like finite element analysis or structural matrix analysis, so that we can more flexibly do these analyses for a variety of building types. The challenge there is just the computational time. We want to be able to make something happen in a very rapid way so that people don't have to wait for these decisions.
So we also had an interesting comment, or at least to me, about the difference between hurricanes and earthquakes. And you don't get a payback period with earthquake. The improvements that you would make to mitigate earthquake damage. Is that because you can't actually mitigate that earthquake damage, or they're just so rare that you wouldn't get a payback period?
So it's also specific to this case study, wherein all they did was put additional nails in the shear wall for that particular housing type. A challenge with earthquakes, the way that buildings are designed to withstand earthquakes, is really, since they're so unpredictable, they just want you to get out of the building, and the building can then crumble. That's how the current codes are based. Versus hurricanes, you have a warning, there's evacuation, so they're designed for a different type of resistance. And so really they want you in hurricanes for your buildings to flex a little bit under the load so that you can run out the door. But what we can also do is look at more complex systems, including damping systems and different materials, in order to really change it so that you're right. There's the probability piece, but if you have a higher probability of earthquake in a particular area, or a much higher cost building that you need to protect, so that that damage would be more significant, then that's when it's going to be useful to invest in some of those more advanced technologies to prevent the overall damage to the building.
I think it is pretty specific to residential homes on the earthquake side. Things beyond in an earthquake, you don't see usually as much damage to residential. I think it would be a different picture for the larger high-rise commercial structures.
Well, there's also the human life issue.
Yeah, which is not account.
It's not accounted for here at all.
Yep.
Right, and the codes for earthquakes are designed to minimize, like, zero fatality is what the designs are there. And so then from there, if that's our baseline, how do we preserve the building after that? Yeah.
All right, thank you very much.